Hi Level 2s and welcome back to 2.5 Organic Chemistry. This is Lesson 5 on Alkane reactions Part B. So we've just been talking about complete and incomplete combustion, and so now I'm going to show you what this actually means. So this is methane gas. So some of you will have used this in various, maybe before, or some people not. The gas we use in our gas taps in the lab is propane. But so anyway, methane, we can combust it by burning an oxygen. Now, how you balance these equations, I'm going to give you a tidbit. This part here, it's all the same. So it's always adding O2, and you always produce CO2 gas, and you actually always produce, that should actually be liquid water. Okay, so sorry, that's a typo there. So from here, how do we balance this equation? So this equation is balanced by first balancing the carbons. So you've got one carbon, so you need one CO2. The next thing you balance are the hydrogens. You've got 4 hydrogens on this side, so you need to do 2 waters here to balance the hydrogens. And then the final thing you balance are the oxygens. So you've got 2 oxygens from water and 2 from CO2. That makes 4 oxygens on the right hand side. So we have to put a 2 here to balance it. So if you follow that every time, you'll end up producing the correct balanced equation. So that's complete combustion. So in complete combustion, you always produce CO2 and water. In incomplete combustion, there are 2 different equations you can do, either producing carbon monoxide and water or carbon soot and water. So it's always water that's produced in all of these reactions. So let's go through the methane one. So if we combust methane, you've got 1 carbon, so 1 CO, 4 hydrogens, so 2 waters, and then this time you've got 2 oxygens from the water, plus 1 from the carbon monoxide makes 3. Now, O2 exists as O2, so to make 3, you need 1.5 O2, or 3 over 2. So 1.5 O2, or 3 O2. 1.5 O2, or 3 over 2. And so that's for this incomplete combustion where there's less oxygen. Okay, and you can see there's less oxygen. 2 oxygens is complete, 1.5 is incomplete. And so if you were doing, again, incomplete, and we were producing carbon, 1 methane produces 1 carbon, 4 hydrogens, you need 2 waters, and then now you've got no oxygens here and 2 here, so we just need O2, and even and here you've got even less oxygen, so only 1 molecule of oxygen. So less oxygen means incomplete, and you get these products here. CO is particularly dangerous. Okay, so what causes it again? Just to recap: complete combustion, lots of oxygen, so lots of O2. We want complete combustion, okay, and when there's incomplete combustion, there's not lots of O2, okay, so less or limited oxygen supply. So I'd like you to pause the video now and try and complete the complete combustion of propane, and I'll go through it now. So combustion, we have to always include hydrogens in our equation. It's better to do an expanded formula while you're learning. So propane is actually a gas. You're not expected to do states at this level, but if you can start picking up on them, it's really good. So to combust means to burn an oxygen, and I asked you for complete combustion, which means CO2 gas is produced and liquid water. Apologies for the typo on the last slide. I've fixed that in your notes for you. Okay, so the first thing we do is balance the carbons. So you've got 3 carbons here, so we need 3 CO2. We now need to balance the hydrogens. You've got 8 hydrogens here, so we need to have 4 waters here. And now we need to balance the oxygens. You've got 3 times 2 makes 6 oxygens, plus 4 times 1, 4, so that's 10 oxygens. So therefore, to make 10, we're going to have to do 5 O2 oxygens on this side, and that is your balanced equation for the complete combustion of propane. And at the end of the lesson, we're going to do something fun, combusting propane. Okay, so that's what we got. Perfect. Okay, so just if you've not put 2 and 2 together, when we use a Bunsen burner, this is a prime example of complete and incomplete combustion. So this is complete. When you have your Bunsen, and you've always done this since year 9, you have the air hole open to get the blue flame and the air hole closed to get the orange flame. So what you're actually doing is allowing lots of O2 in when it's open and less O2 in when it's closed, and so it's actually incomplete combustion when we do the air hole closed. Okay, cool. So we've done combustion, so now we need to move on to the second type of reaction that alkanes undergo, and that's called a substitution reaction. Okay, now what is a substitution reaction? So a substitution reaction, I'm just flicking to the next slide to show you the definition, is when one atom or a group of atoms is replaced by another atom or group of atoms. Okay, so when one atom or group of atoms is replaced by another atom or group of atoms. Now at level 2, what we're doing for substitution with alkanes is we're going to add a halogen. Now your halogens exist as diatomic molecules, so it may not have been Cl2 here, it could have been Br2 or I2 for instance. They always exist like this. And so we can react these two together, and literally what happens is one atom, which is in this case the H, gets substituted for a chlorine, and you can see that there are two products produced. This Cl2 breaks in half, the chlorine jumps on, and the hydrogen comes off forming HCl. Okay, so if that had been if this was Br2, then it would have been a Br here, and this would have been plus HBr. So this is a substitution reaction because the hydrogen is being substituted for a chlorine, and what you'll have realized we've made is a haloalkane. So we've gone from a alkane to a haloalkane, and how do we do it? Via substitution. Now this reaction is very slow, and there's one other thing that you need to know for this, that this reaction requires a catalyst in order to speed up the rate of the reaction, and that catalyst is UV light. So if we tried to do this reaction in a dark cupboard, don't know why we would, but if we did, nothing would happen. Okay, so we need to put it out into the sunlight. The lab is actually okay, but it does take a bit of time because it's a slow reaction, but it will react. Okay, so this is a substitution reaction, and actually this can continue as well, just so you know. So once you've actually substituted once, because there's other hydrogens, if you've still got some excess chlorine, for instance, it can then substitute another, and then it can substitute another from there, and so forth, and it can continually substitute until you've got no spots left to be substituted. But you're not really going to get asked any of this at level 2. They're just focused on the first substitution part. Okay, so we've talked about the definition. You do have to know this definition off by heart. It comes up a few times. So substitution is when one atom or group of atoms on a hydrocarbon chain are replaced by another atom or group of atoms. And you'll see why I keep saying group of atoms when we get to another topic where substitution happens. Now in level 2, it's always going to be the end hydrogen. So here is propane. And when we mean the end hydrogen, we literally mean we only switch the one on the end. This is not technically correct, but this is the hydrogen that is always removed at level 2, the end one. They keep it nice and easy, and so therefore if a substitution reaction happens with, say, Cl2, then you end up with a chlorine on the end, like so. So nice and easy. That shouldn't probably confuse any of you. Just to kind of show you that actually there is a different rule that happens here to work out what should happen. Now again, this is not what you're going to get assessed on, but it's quite good to know. There's like a wee general rule, which is the poor get poorer. Now you're never allowed to put that in an exam because we do deal with this rule somewhere else, which you do have to use. But it's simply that the carbon with the least number of hydrogens loses another hydrogen, and the Cl will replace it. So that means that if we look here, you can see that this carbon on the end has 3 hydrogens and the carbon on the middle has 2. So technically this carbon is poorer. Okay, so this carbon will actually lose this hydrogen more preferentially. Now this one can also be lost as well, or one of these ones on this carbon. By the way, these are all equivalent, so it doesn't matter which one. So this one will actually come off most of the time, but this one will also come off. Now that's the same as this one. So these ones coming off are identical because it reads the same forwards and backwards. So just remember that. So the poor get poorer because our middle carbon's only got 2 hydrogens, but our carbons either side have got 3. Technically this middle carbon is poorer, so it's going to lose its hydrogen, and so that's actually what happens, and that's called the major product. The one that forms more often is the major product. So you can see here that middle carbon's got the chlorine, okay, and it's lost a hydrogen, and it's the major product. So the carbon with the least number of hydrogens, in this case the middle one, because it's got 2 versus the other ones have 3, loses another hydrogen, so gets poorer, and that forms the major product. And major just means that's the one that's produced more often. The other one will happen where the hydrogen comes off, one of these terminal hydrogens come off, but that happens less often, and it's called the minor product. Okay, so at level 2, we always actually just do the minor and put it on the end carbon. But just so you know, if technically the correct way is that the pore get poorer, so the carbon with the least hydrogens would lose another. So what do substitution reactions involve? Okay, they involve breaking a CH bond and forming a CBr or CCl bond. Sometimes they'll do adding iodine, and so there'll be a Ci bond, but it's not very common. Now, an H atom is removed from the molecule. Okay, that's important to know. It requires UV light, and it's very slow. Now, there's one thing that's quite useful, and that's the fact that one of these reactions involves a colour change. When we add bromine, we add it in the form of bromine water, which is just BO2, and it's been dissolved in some water. Now, BO2 is an orange, Br2, is an orange compound, and when it forms just a singular Br atom with say hydrogen or on a molecule, it is actually colourless. So there's a colour change associated when we add bromine to one of these molecules, which is really useful because it'll initially start orange when you add the solution of Br2, because obviously the Br2 is intact. And as the Br2 reacts and forms this molecule and the haloalkane, it'll lose its colour and it'll turn to colourless, which is quite cool. So here's ethane, for instance. So when Br2 reacts and a substitution reaction happens where a hydrogen atom is substituted for the bromine atom, this is orange. So when you add it, the whole thing will look orange. And as this is produced and HBr is produced, and you've got no more Br2 left, it'll turn colourless. So which is pretty cool. And you can see here, if we've got propane, remember the pore get poorer, so you'll actually get two products, your major and your minor product. The major is when the pore gets poorer, so the hydrogen with the least number of hydrogens loses a hydrogen. And so this one here, this has got 2 versus either side's got 3. So this one in the middle is going to lose a hydrogen to produce this compound most of the time, 97% of the time. And then it can also go on the terminal one, but that doesn't happen as often. And it wouldn't matter if we'd done it on this carbon or this one, because it reads the same forwards and backwards. And you can see the same again, okay? So these 2 middle carbons, again, it doesn't matter which one because it reads the same forwards and backwards, but they've got 2 hydrogens, so the pore get poorer. The bromine's going to go on one of them, doesn't matter which one, and that'll be the major product. And then if it was one of the terminal ones, doesn't matter which one because it reads the same forwards and backwards, that's the minor product. If you look here, it's quite clear that there are 3 carbons that have got 3 hydrogens, and this one in the middle's got 1, pore get poorer. So this one in the middle is going to lose another one, and the bromine's going to go there, and that happens most of the time, 99% of the time, and only sometimes would it go on these end ones. So I hope that makes sense. Okay, so here's another example of chlorination. So it's all substitution is one of the H's come off and a halogen goes on, and you end up producing a haloalkane, which is quite cool. Okay, there's always a secondary product, so HCl or HBr or HI. Okay, and it can happen with cyclic structures. It's just that at level 2 we don't really deal with cyclic structures too much. The only reason why I put it in here is because cyclohexane is a liquid at room temperature, so we often use cyclohexane when we do practical work because it's easy to use, and so you might see a substitution reaction of cyclohexane with chlorine, and I think we're doing that later on today, and so one of the H's gets substituted with a chlorine. Cool, so we're going to do this practical today, and your homework is to do SciPad pages 145 to 146. Thanks for listening, everyone.